we are going to do supervised machine learning. Supervised learning. And actually what we will do, we will use something called linear regression. So we will build a we will talk about linear regression, and at the same time we will build some kind of machine learning system for some task particular. And so this is a supervised learning. So what's the goal? We want to take some. So what we will do. So the example that we will be working will be we want to predict prices of flats so you want to buy our apartment. We want to predict price of apartments based on what would you say would be a good parameter for. How is for example, how big is the apartment? Is the basic, I mean, if you look at any market, basic parameter that you want to look at is how many square meters the apartment has. Okay? So we want to predict prices of flats based on size, square meters. So so basically we have only like data, like one parameter, okay, so, and we would like to, from this one parameter, we would like to say, okay, this apartment should cost, I don't know, 30,000 euros. There is no apartment for 30,000 euros. 130,000 euros. Okay? So, if you look at it a little bit more formally, what you want to do is, if you just don't have just one parameter, you want to have multiple parameters, right? Maybe you don't only want square meters, you also may want, I don't know, whether it has a reconstructed kitchen, where it is located, things like that. So you might have multiple parameters. We will encode these parameters as features, and each feature is basically a real number for us at the moment. So basically, for what we are trying to do is you have something. We will have some vector called xi, and it will have basically n real number. It will be basically a vector of n real numbers. Okay. So these are input features. And in this particular case, this is just a single number. Okay? So vector, very, very simple vector, just with one number. Okay, good. There will be lots of these things, like, I will say a matrix, and then I will talk about one by one matrix or something. So now we are talking about one vector with one variable. Okay? But in general, you have vector of values. And what would you like to do is you would like to predict something called target variable, and this is also a real number. Okay, so in this case, this is the price of an apartment. So, and we will call this target variable. So, and so what would you? That's what we want to do. I mean, in the end, you would like to have some kind of predictor that would take these input features and give us the numbers, give us the target price. So what else do we need? Or how do we formulate it as some kind of well-formulated problem?
Curve fitting.
Sorry? Okay, you said curve fitting. How do you formulate curve fitting as a well-defined problem? Okay, that's very good. Based on what? I mean, what we are fitting? Yes, we have to have some kind of training data. Okay. So the first thing that is given. So really the task that we are going to do is that we will have some training data. So given some training data set, And this training data set looks like what?
A list of houses with prices.
Okay, so in this case, what you need to have, you have to have like features of these individual apartments and target price and their real prices. Okay, you have a training set that looks something like that. So x1, y1. So this is the pair, right? The feature vector, and then the target variable. And this is like this feature vector now is very degenerate, right? Only one number, but doesn't matter. Okay. So, and you have multiple cases. So let's say you have T training examples. One note on notation. I will be very bad with notation most of the time, which here really means, I mean, when you are talking about vectors, you usually try to mark that this is a vector. I will never do that, okay? So you have to figure out from the context what is vector, what is just a single number, whatever. Okay, good luck. Okay, so now we have, so these are pairs, this is a vector, this is a target variable, okay? Good. So you said some kind of curve fitting. We are talking about linear regression that tells you that the core curves that we will be using won't be that complicated at the moment. So basically what we will be trying to do, right? This is the square footage of the square meters of the apartment, and this is the price. And we have these training examples. They might look something like this. Okay? And what would you like to do is you would like to basically fit some curve. In this case, you would like to fit a line through that. So you would like to say, this is something like my predictor. And if you look, and then if you are looking at whether some kind of price is appropriate for an apartment, you look at the square footage and you see, okay, so maybe this is the price for the apartment. So how do we? So how do we formulate this in some better way? Not just by talking about yeah? We need some kind of penalty function. Okay, so what we are training, what we want to do is we actually want to choose some kind of target function. Okay? This is the function that will be later used as a predictor. So that's the first thing. So and we need to say, and we are not allowed to use, since we are using linear regression, we are not allowed to use any kind of function. We need to use function from some special class. Okay? So the second thing that is given is called set of hypotheses. Okay, so this is the set of functions that are allowed. In this case, we just want to use linear functions. So these are, so this is some kind of set of function. So these are functions from this feature space in target, right? And in this case, we will use linear functions. So this will be simply a linear combination of individual features from the vector, from here. Okay. Okay. So here we use linear functions, and our goal is, so another thing is that what you say, we need to we somehow want to find the best function possible, right? But what is the best function? And that's defined by some kind of error function. So for every, so if you take any function, you can compute some kind of error, and then you choose the one with the minimum error. Okay? So the task is to find a function h from this set of from this hypothesis space that minimizes some kind of error. So basically, probably you want to take you want to go through all training examples, right? And you want to say, okay, so if I put vector xi to my function, it will give me some value, hxi, right? And I want to compare it with value yi, this is the target value. And so and I want to find from all the functions, from all of these functions, I want to find the one that is minimizing this error. And in our case, so this is just the two values, right? So I will denote it like this. I will use simply so this is the difference difference between the two values. You would like to, I mean, some of you maybe would suggest that just use the difference, but the problem is that, you know, some of the values are positive, some of the values are negative. If you sum them up, then it's going to be a big mess. So big error on one side and big error on the other side would cancel out. So you need to do something to make sure that all the errors are positive, and this is one of the ways of doing it. If you square it, then that's fine. There are other ways, and we will be discussing them later. Okay, so how does it relate to our particular example? So here we have just one feature in the feature vector. Okay, so this is just the square meters. So basically, I get a training set, square meters price, square meter price, square meter price. How would you get such a set? If you just wanted to do this right now, go to the website like Realities or something, and just scrape the values from the. You have square footage, you have a price. It might not actually be that good idea, but let's keep that for later, because the data would probably not be very representative. But anyways, okay, so we would somehow. So this is one way of getting this type of data. So you get training examples. You set your set of hypotheses. In this case, these are linear functions for one attribute. These are what? These are just functions. So let me just change the color. So basically, for our case, you would like something. You would like to have functions that would depend only on a single parameter theta. I would put it here. Okay, and this is basically a function that looks like actually two parameters. Sorry, this is vector. I caught myself. Okay. So this is actually vector of two values, theta 0 and theta 1, and basically this is the kind of function that we want to track. And I take all of these possible combination of theta 0 and theta 1. I want to find the best one that fits the training set best. And fitting best means going through this, using this square this square of the difference. Any questions so far? So basically, what this all translates to, some developing like two things at the same time. I'm developing this one example that we are working on, this very simple one, and I'm also developing the sort of general framework at the same time. That's why it's so complicated and messy. So basically, but what it translates to is you just want to find just want to run something that will try to find two values, theta 0 and theta 1, nothing else. Okay. So we want to find two values, okay? Find theta 0 and theta 1. Now I'm switching to the example, minimizing the error function. I will call this error function J, which is basically sum of h theta xi minus y squared. And we can, so basically this is theta 0 plus theta 1 x minus y squared. So any suggestions on how to find such theta 0 and theta 1? This is, now we have turned like a rather vaguely formulated problem into something that is actually, that has actually maybe unique answer, or not necessarily unique, but there may be several combinations of theta 0 and theta 1 that actually minimize, that have the same error value. But basically this is a well-defined problem. So now let's forget all about fancy machine learning and just try to solve this well-stated problem.
Minimize the theta function, so we have derivative of theta 1 and
Okay, so all of you have sometimes seen how to find the minimum of a function that has one variable. Okay, you take the derivative and you try to find the values where derivatives gets to 0. It is a little bit more complicated for functions that have like multiple values. Okay, so some of you didn't have this, but it's actually very similar. So what we are trying to do, we are trying to find extreme values of multivariate functions. Actually, how you do it is very similar to what you do in the case of one variable, but you, instead of regular derivatives, you need to use something called partial derivatives. And there is lots of things that you can learn about partial derivatives, but for us, the most important thing is that partial derivatives are just that you get them the same way as the regular derivatives. Basically, what you do is you choose one of the variables, let's say theta 0, and you treat the other variable as constant. Okay, so if you parse this definition and compare you to the definition of regular derivative that you have had like 2 years ago maybe in some class, then you see that it's essentially the same definition. And to demonstrate this, if you have like function like this, and you want a partial derivative according to x, then okay, so this is x squared. So derivative of x squared is to 2x. This is y squared. I've said treat y as constant. So imagine this is 7, okay, and derivative of constant is 0. And then this is xy again. You treat this as a constant. So imagine this is 7x, and then you would get a 7 here. So this is y. And you could also do the same thing and do partial derivative according to y. And so in the single variable functions, you had this rule that if you wanted to find the minimum, find a place where the derivative is 0 or maximum. Actually, it's not clear which one is which. And this is one of the things. And those who are a little bit versed in calculus know how to find whether it's minimum and maximum. And we won't talk about it. Okay. So most of the people in machine learning, if they take derivatives and they want to find the minimum, they just set it to 0 and they say, yeah, okay, it will. Since I'm trying to find the minimum, that's probably a minimum. And sometimes they make mistakes this way. So we will do it that way. We will skip these all verification steps, but you should do them. Really, you should do them. We won't. Okay? So basically, but the main thing that we will be using, if the function has a local extreme at a particular point, then all partial derivatives must be at this point must be 0 at this point, and the point should be internal. I mean, I'm not talking about like if you have doesn't matter. Special cases. Don't worry about special cases. Any questions? So let's do this exercise here. So what we need to do, we need to compute two things. We need to compute partial derivative of this function with respect to theta 0, and the same one with respect to theta 1. Okay. Okay. One important difference. There is difference in notation. Partial derivatives have this delta instead of d. Okay. So let's try this. So we are trying to find the partial derivative of this function with respect to theta 0. So this is sum from I is equal 1 to t of h theta x I minus y I squared. And so this is, so we need to rewrite this a little bit. So this is basically theta 0 plus theta 1 x. So that's the xi minus yi, right? Squared. And so what's the derivative? Okay, so I claim that the derivative is 2 times theta 0 plus theta 1 xi minus yi. Is that correct?
I think so.
Sorry?
It's the theta j to theta 0. Just it is missing.
What's missing?
For all the sum signs, I think there is missing the derivation function. No? Line.
Yeah, of course. You're right. Okay, so this is right. This should be like this. And now it's no, and now it's okay. Yeah. Now it's correct. Okay, so basically this is 2 times whatever is in the times the derivative of what is inside. Okay? Okay, and I want this to be 0, right? So if I take this, I want this to be 0, I get 3 times theta 0 plus theta 1 sum xi minus yi should be 0. Okay, so I have divided this, I mean this 2, I have divided everything by 2, and then like this is the same element, it's there 3 times, right? This is in the sum, so this is this particular thing. Then theta 1 times sum of all of these minus sum of all of these. And this should be 0. Okay, so this is one thing. Doesn't still tell me what theta 0, theta 1 should be. But fortunately, I also have the second thing. So I also need to do partial derivative according to theta 1. So it's the same exercise basically. I will just write it down. Okay. So it's sum 2 times theta 0 plus theta 1 xi minus yi. But now there will be also xi here. Why? Because you are doing derivation of this function, but not over theta 0, but over theta 1, theta 1. And now you have so this is 2 times this thing times derivative of whatever is inside. And derivative of what is inside is xi because there is theta 1 xi in here. The other two things are constants. Okay? And this should be again 0. So from this I get theta 0 times sum xi plus theta 1 times sum of xi squared minus sum of xi yi, and that should be 0. So what's the next thing to do? Okay, I have these two. Basically, by doing derivatives, I have these two equations. And if you look at it, this looks complicated, and it has like some squares in it and things like that, so that doesn't look good. But you need to figure out what are the variables and what are the constants in this case. Variables are theta 0, theta 1, so they are here, right? And everything else is a constant. Regardless, with respect to fixed training set, these things are constants. So this is basically a set of two linear equations with two variables. And you can solve this system of two linear equations of two unknowns. And what you get is you get theta 0 is equal if I didn't make any mistake. So this is 1, and theta 1 is t times sum xi yi minus sum xi sum of yi over t times sum of xi squared minus sum of I squared. From these two to this one? So basically what would you do most likely is, it's the high school stuff, right? You go and, I didn't do all the
Yeah, but I didn't see what was right. I understand what you did, but I can't say that.
Okay, as long as you believe me that the solution to this set of two linear equations of two unknowns is this, who understands what's going on? Okay, there in the back. Question. Okay. So the misunderstanding there was whether why are we doing this in this relatively cumbersome way if we can do it better with some knowledge from linear algebra. That was the suggestion, right? Please keep this slide for next 2 minutes, and then we will come back to it. Okay, any other questions? Yeah?
How do I know if my training set is good for fitting to this linear regression?
How do you know?
Like, I have this training set, and how do I know that the linear regression is good for it?
So you are asking whether linear regression is a good fit for this problem, particular or?
Not this problem, but in general, I have good data, and I want to know if I can use like only line.
Okay, so that's the question that we will answer about 3 lectures from now. Okay? It's a very good question, and we will get back to it. Any other questions? Okay. So, it's okay, we can now solve this problem. So basically to summarize what we can do, if we want to predict prices of apartments from their square meter, from the size of the apartment, we can simply collect the loss, collect the training set of lots of sizes and target values. Okay? That's training set we absolutely need. Then we said we want to fit a linear function, and right, as long as we have this training set, we can compute the best linear function in this way. Whether it will be a good predictor in the end, that's a good question. We will, as I said, we will come to this question. Maybe we want to fit the quadratic functions or cubic functions instead of, or something completely else to this. Okay, but we will come back to this later. Good. So now also, apartments don't only have like these, like square footage. They have lots of other parameters. So perhaps let's add one more. What would you do? So now you have 2 features and 1 target variable. So what would you do? Also, so one thing that we could do. Sorry? Same approach would work. So we would like, so we would like take pull up our sleeves and go and do repeat the same thing again. This is not 2 variables but 3 variables, and would get slightly complicated things here, and we can do this for 100 variables and so on. But this is also mindless computing. That's what we are going to do, but we are not going to do this particular. You can already see here that this is a pretty complicated formula, and they are not getting any less complicated with number of variables. So there's it's messy if you don't use any additional knowledge, and the knowledge that we will use. So basically what we will do, and the reason why we are doing this is that lots of the machine learning algorithms are actually not done in a single variables, but instead they are trying to write everything as a sort of in a language of matrix multiplication and things like that, so that they can easily use all the tools that algebra gives you to actually work with this. Yeah, okay, so everybody knows what matrix multiplication is, fine. Okay, so but basically how you get this value is that you take and multiply everything in the first row with everything in the first column. Okay, so 1 times 2 plus 3 times 0 plus 1 times minus 1. And so on. You get all of these values. It's very simple. Okay. Who knows what inverse matrix is? Okay, great. You can skip this. Who knows what transpose matrix is? Great. You can also skip this. But one thing that we need to know, or that we need to, I want to remind you, is that if you take and you multiply 2 matrices and you take a transpose, it's the same as multiplying the 2 transposes of the 2 matrices, but you need to treat this reverse. Okay, so it's not I guess the point is that it doesn't, even if you are multiplying square matrices, it actually does depend on what order you do it. So let's try to formulate all this as matrix multiplication in the matrix multiplication framework. So, yeah? Okay. So default orientation of vectors will be vector is a matrix with one column. Okay. Okay. So hypothesis space, linear functions. What is hypothesis space in this case? So this is some kind of set of functions H and these functions look like what? So you can think about it. I mean, you have a vector which is a one column matrix, and you have some kind of and you need to do linear combination of all of these values in the vector. So how do you do that? So this is a simple like a matrix multiplication, right? You have some vector of parameters. So let's I just marked the vector. I shouldn't do that because it gets spoiled. So this is if you have something like this, so you have simply a function that looks like, you know, right? So you take ith value from theta and ith value from the feature vector x. We will get back to that. And this is simply you take the vector x, you transpose it, and okay. And there was a question. Because there is also in linear functions, there is also usually that we are having a linear combination of the input variables plus something. How do we get the plus something in there? You can actually write it explicitly, but it will break, I mean, it will be ugly then. So what we will do, we will extend the feature space. We will add one more feature space. And basically, for every vector x, there will be, you know, x1 will be 1. Okay, so the first feature of every example will be fixed at 1. So actually in this case, in this previous case, you would not have a single vector of like just a single value. You would have values like 1 and square meters of the apartment. That would be the input vector. Okay, so we have our hypothesis space. So these are all functions that look like this. Then training set will look like, actually, you can say that the training set is a set of vectors, but for reasons that will be apparent in a minute, we will actually do compose these vectors into a matrix. So there will be one matrix that will look like this. So this is the first example, and there is also this one in here. Okay. Second example, third example, and so on. And the last example will be here. So this is matrix, which looks like this, and it actually has a name. It's called design matrix. And we will usually denote it as X. And it has T rows and columns. And now I include this extra extra feature in the number of columns. And then you also have a corresponding target vector, which is basically target values. Okay, so this is target vector with t rows and 1 column. Now the next thing that we need to do is we need to formulate the same problem as before, something like this. So we have this error function, and we want to find the vector theta of these values, so that we minimize this error function. So how do we write it down? So I will have this function j theta. So this is simply sum over all training examples, right? And we know that we have this xi transpose times theta. That's the value. That's what you get when you apply that's basically what you get. One real number that you get by applying the function with parameters theta to the vector xi. And we want this difference, right? And so now, I would like to compute all of this at the same time. So what I do, I play a little bit, and what I get is, I get this thing. If I take the whole design matrix and multiply it by theta, what do I get? I get a vector of all predictions, right, for all the training examples. So I take this, I take and subtract y from it, so then I get what? I get basically a vector of differences. So what I need to do next? I need to somehow square all the values in it and sum them up. How do I do that? Sir?
The length of vector, you just take the part of the vector.
Yes. So basically, this means I can write it this way. So this is the same thing. And so what I want to do is I want to find vector theta that minimizes this thing. Okay, so what do I need to do next? I need to take all the partial derivatives, right, of this. Well, fortunately, there is also a more friendly notation for that. So the thing that we will be working is called gradient. So here, I will be using gradient as follows. So I can have for technical reason, I will think of functions not only as functions like that turn a vector into number, but also I will generalize this function to any function that takes a matrix and turns it into number, which is the same thing actually. Okay? So if I take a function and it takes like a matrix of some values, it's the same linear combination. It's just So if I take this function, I can take gradient, which is basically a matrix that has all the partial derivatives in it. Okay? Why am I doing this? Because this is the kind of compound notation that will allow me to actually compute all of these at the same time and more quickly or more easily than think. So these are the So these are the things that we'll be using in derivation. So now what we want to do is we want to take gradient. So in this case, we want to find the vector theta of where gradient basically results in a zero matrix, right? This is what we want. We want theta such that. Okay. So let's start doing some. Computation. So this is gradient over all theta x theta minus y transpose times x theta minus y. The only thing I've done is I've expanded this function here with this. Okay? Okay, so now I know that this is what I will use this thing. I will like put this transpose inside. Okay? So this means that I will have theta transpose times x transpose minus y transpose. So I had to reverse the order here. Okay, so now what I can do? Well, I mean, it's always easier to do the derivations if I just multiply things inside the brackets, right? So I expand this. So this will be derivative gradient of theta transpose x transpose. This is this particular times x times theta minus theta transpose x transpose y minus y transpose x theta y transpose plus y transpose y. Pretty.
Just use the fact that this connection. You'll use the distributivity and
Yeah. Okay, yeah, I'm using. But pretty much this is straightforward, more or less. There are some things that you would need to prove. If you didn't have any algebra at all, if you didn't, it's just a reminder of what some of you had like 2 years, 3 years ago, so you don't remember necessarily. Okay, so any questions about this so far? This is just easy, multiply all the things. Okay, so let's look at this particular thing. What is gradient of this? Y doesn't depend on theta in any way. We know that if you want to take derivatives of something that doesn't depend on the variable that you are on any of the variables that you are derivating on, it's zero, right? So this is going to be zero. You can omit this. Okay, another thing. Okay. Now I am going to use something called trace. So basically, the trace of the matrix, you go through the diagonal of the matrix, and you sum all of the values. That's the trace. And there are some interesting things that go on with traces and derivatives. So in particular, if you take traces of the, if you take traces, if you take derivative of the trace of a matrix, then you get something like this. Okay, let me write the next step and let's explore it. So I claim that if you take this, that this is the same as the okay, so what is this thing in there? What's the dimensionality of these things inside? Oh, so let's take some of these matrices, right? So let's say this one. So this one has, what dimension does it have? So this is theta transposed. It has what?
Number of features is
Yeah, number of features is n. So this is something like 1 times n, right? This x transposed, what's the dimension of this? So this is n times t, right? This one is t times n, and this one is n times 1. So the result is 1 times 1, it's a number, right? Which is what we would actually expect, because j theta is actually a function, regular function. So it takes and it has like the output is number, right? So this is number, this is number, this is number, everything is number. So what I was telling you, that when I will be talking about matrices, suddenly it will turn out that I'm talking about 1 by 1 matrices. This is here, right? I'm talking about, this is like something that is not necessarily apparent, but these are all 1 by 1 matrices. So these are all basically numbers. And what is trace of the 1 by 1 matrix? Is the same thing, right? So I can just put trace in here. Why not? I mean, it's the same, right? Okay. But now I have these interesting claims, these two, that will actually help me to go forward. So these are sort of some kind of equivalence of some of the rules that you know from regular derivatives. But we won't go into them. You can actually go and try to prove them. It's very easy. You just write everything down, like expand all the notation, and it will be there. It's not difficult. Okay, so what we have here. Okay, let's go. So first of all, if you have sums, then you can sort of expand, put things together. So you have, so this is equal to trace of, okay, you have this theta transpose x theta, okay? So this is one, and this goes through, this is theta. And minus, and I claim that this number and this number is the same. Why is that? These are just two transposed two matrices that are two matrices 1 by 1 that are transposed. 1 by 1 matrix that is transposed is the same thing. Okay, so we have minus 2 times gradient theta transpose x transpose y. Okay, then and trace. Okay, let's go further. So now we start pattern matching. Anyone who sees how to use any of the rules that are here? So you can, for example, have this can be B, this can be A, this is A transposed, and that could be, I mean, here you have almost the same thing, A transpose B A, okay? But you also have to have some matrix C. What would you do? Yeah, identity matrix, right? So put here, well, yeah, okay, but I want matrix. It's number one, but it's one by one identity matrix, right? Okay, so let's take this, and now I can use this rule, which is there, which is so this particular thing should be B transpose, so it's X transpose X times A, which is times theta, times C transpose, which is identity, so I don't need to even write it down, minus B times, so this is X transpose X, A, this is theta, A plus. Okay, good. Okay, so this thing, this part is this thing. We just didn't done. We have just done all the derivatives now. Okay, and this thing you can do from this first. So there is a, if you have a theta here, theta is A, right? So this is yeah. Okay, so I will do transposition of this. Okay, so this thing is equivalent to Y transposed X theta. I hope I done that right. Okay, and now this is A and this is B. From this rule over there. So I have plus B transpose, which is X transpose Y, and vice. So I have 2 times X transpose X theta plus 2 times X transpose Y, and that should be 0, right? Yeah?
There is probably there should be minus 2x transpose y.
Sorry?
There should be minus 2x transpose y because minus
Minus. Yep, you're right. And that should be also here. So in other words, what we have got is that we should find to minimize this thing, we should find a vector theta that minimizes this thing. X transpose X theta is equal X transpose Y. Okay, so let's look at what is this. What is this? What's the dimensionality of this of all these things? So this is, so matrix X has what dimension it does have? So it has m times t, right? T times n, yeah. T rows, n columns. Now this one is the same matrix transposed, so this is n times t. So together, this gives you a matrix that is n times n. Okay? So now so what is this? This is X transposed again, so this is n times t. And this is t times 1. So this is n times 1. So basically you have some n by n matrix multiplied by some unknowns. So this is like, with regard to particular fixed training set, this is fixed, right? This is a constant. There's nothing variable in here. These are, theta is something that we don't know. So this is n by n matrix times a vector of n unknowns is equal to some constant vector. You know what that is?
System of linear equations.
This is n linear equations with n unknowns. Okay, so we have n linear equations. With n unknowns. So what will we do? We just solve them, right? Call the library that solves them. Gaussian elimination or whatever. And when you solve them, you get the values of that.
If we solve the right.
Special cases. That's the, I mean, we don't talk about special cases, it's forbidden. Well, in reality, what you do when you can't solve the main, it's not very usual that you actually can't solve this.
Is it possible?
Yeah, no, most of the time, this like real data, not really designed to produce a system that cannot be solved. You get a single solution.
So my question is it actually possible to create a system that doesn't have a solution? I understand there might be infinite solutions.
I think it's possible to create a system, and as long as you have a very small number of training examples,
That has zero
And-
solutions.
like one training example.
I understand you can have infinitely many solutions.
Then you have infinitely many. Yeah, I guess, but then this would also.
Basically, when the dimensionality of the data set is lower than zero.
Yeah, I think you can get some weird cases when this cannot be solved.
If
Like,
it's not-
I think if you have like all the training examples like on one line, that is,
Yes.
you know, something like this.
I understand that there are
You do it.
infinite solutions. My question is whether it is possible that there are zero solutions.
I think this is it. Let's think about it offline, okay? I don't actually know, but I think there are some cases, and in these cases you just perturb the values a little, and then you get the solution. Okay, so basically, to summarize all of this, what we have learned today is how to do linear regression, right? Because, like, we have built our first machine learning system. Because what we have some training data set, right? Training data set can be expressed as this design matrix, which we don't have here anymore. So basically all the vectors, all the training examples as a rows of the design matrix, and you also make a target vector. And then so this is the training example. We have chosen the set of hypotheses which are linear functions. For some of you, this might seem that it's very limiting, but in fact, we will see some tricks. I mean, you could try to do this with quadratic functions and things like that, but there is a trick that will actually allow you to avoid all of this. I mean, you only need a linear regression, in fact. You don't need anything else. And we will see why is that in one of the next lectures. So right now we have chosen the set of hypotheses that are all linear functions. This is describing the algorithm that will allow you to find which linear function actually fits the training data best. So basically you create a one matrix, compute one matrix, one target vector, and you solve a system of n linear equation of n unknowns, and you basically have your function, and then you can go and apply this function to new examples as they come along. Use it as a predictor. Okay, and I think okay. So this is called. Sorry, I wanted to still tell you. This is called normal equations. This set, the set of equations. Okay, any questions?
Is this black magic?
No, we are not into black magic yet. This is not black magic. This is we will do black magic here, but this is not it. This is like perfectly easy so far. There is actually, I mean, every step that we have done today, more or less, you can actually, you know, I have taken lots of shortcuts, but you can actually sit down and work out all the shortcuts, and it's very straightforward, just from definitions and everything. So there is no black magic in here so far. Any questions? And in fact, what we will do lots in this class is, you know, you have this machine learning world, right? The black magic of today, and we will take lots of things from this machine learning world, from this black magic, and just show you how exactly the rabbit got into the hat. So that's the purpose of this class. Okay, so if there are no questions, thank you very much. And on Tuesday, there will be Vlado Božar giving a lecture. On Wednesday, there